So, welcome everyone to the lecture 12 of the course on ecological economics. In the last two lectures, we examine abiotic and biotic resources in depth. Today, we step back and ask, how do we think about the systems that these resources are part of? So more like a macro view. The answer lies actually in something called systems thinking, and specifically in three interconnected ideas, which is feedbacks, threshold, and resilience. But before we move into that, let's first try and understand what is a system. Okay, what exactly is a system? So a system is, in the technical sense, which is used by Meadows, Donella Meadows, and other systems thinker, is a set of interconnected elements that produces behavior greater than the sum of its part. Like something which we discussed in the last class, like how if you look at one tree, it doesn't give you much idea, but when you look at the Amazon as a whole, it tells you gives you a better understanding what ecosystem function or services they provide. So similarly, we say that system is therefore it's an interconnected system, and that kind of produces certain kind of behavior, which behavior as a whole is more important than sum of its part. Now, there are three components to every system. The first is the elements, the visible, tangible parts. These might be trees in a forest, rivers in a watershed, firms in an economy, or even household in a community. These are elements. Second, the interconnections, the relationships and the flows between those elements. These are often less visible than the element themselves, but they are far more important for determining how the system behaves. And third is the function or purpose, meaning the behavior the system produces over time, which often emerges from those interconnections in ways that no individual element intended or could predict. Right? So remember these three. The first is the element, second is the interconnections between the element, and fourth is the function that they play. Third is the function that they play as element and given the interconnections between them. Now, the most important insight from systems thinking is that you cannot change just one thing. When you intervene in a system, when you change one element or one interconnection, the effect ripples through the whole network of relationships, and it often produces consequences that are distant, delayed, and entirely unexpected. So the classical ecological, illustration of this is what happened when wolves were reintroduced to Yellowstone National Park in the United States. So this is a very classic example. If you want to know more, you can actually also look up in other, in the internet as well, what exactly happened. So just to give you a brief of it, that when wolves were removed from the ecosystem decades earlier, deer populations exploded. Okay, with no predators, deer overgrazed the riverbanks, stripping them of vegetables. Without vegetables or without vegetations, the banks eroded. Eroding banks changed the course, the characteristic of the river, because of which fish population declined, because their habitat were degraded. When wolves were reintroduced, because they were removed, so all of these happened. Now the solution they felt was that let's reintroduce. The entire cascade then reversed, not just because wolves ate deer, but because the fear of wolves changed where the deer used to graze, which allowed vegetation to recover, which stabilized riverbanks, which improved fish habitat. This is called a trophic cascade, and it demonstrates exactly how deeply interconnected the elements of a system are. A single species reintroduced transformed the river. Imagine, so if you removed it, it transformed so many things. You introduced it, it again transformed everything. That is what systems thinking prepares us to expect and understand. So this is why we say the element, the interconnectedness, and the function. So if you choose, or if you pick up one element and remove it, it can actually destroy not just the interconnection, but also the functions that they play together. Now, the next thing to understand is the feedback loop. The interconnection in a system are not just passive pathways. They carry feedback. And understanding the feedback is central to understanding why systems behave the way they do. So there are two fundamental types of feedback loop. The first is a reinforcing loop, sometimes also known as a positive feedback loop. So this is self-amplifying. A change in one part of the system produces more changes in the same direction. The result is exponential growth, or growth or exponential collapse. So reinforcing loops are behind compound interest, behind population growth, behind spread of viral disease. So one person gets COVID, many got COVID, right? So that's something called the feedback loop. They are also behind some of the most alarming dynamics of ecological system. So consider what happens to Arctic sea ice as temperature rise. Melting ice exposes dark ocean water, which absorbs more solar energy than the reflective white ice did. So this causes more warming because it is now taking more solar energy, which will cause more increase in or more warming. The feedback then amplifies itself. So basically without so this more sorry, I just forgot to tell you one thing. This, since this causes more warming, which causes more melting, which exposes more dark water, then it causes again more warming. So you see the cycle. So the ice melt leads to more exposure of dark ocean water, which is consuming more solar energy, leading to more warming. And this more warming is again causing another level of ice melt, sea ice melt, which is again causing much more warming. So this is like a loop. The food feedback loop, like feedback amplifies therefore itself without some counteracting force or a reinforcing loop to carry a system further and further from where it started, in this case towards a state with much less ice. So this is called the feedback loop. The second type is a balancing loop, sometimes called as a negative feedback loop. This is self-correcting. The system resists change and seeks to return to equilibrium. You try to change it, it tries to resist and tries to come back. A thermostat is the textbook example. When temperature rises above the set point, the cooling system gets activated. When it falls below, the heating system gets activated. So this is what a thermostat does, right? What it does is that when it is too hot, the cooling system gets activated. The thermostat tries to bring it back to the normal temperature. And when it is too cold, it basically it tries to activate the heating system and brings back the temperature which is most required. So the loop balances around a target. There is a target that this is the good temperature to maintain. If you look at the predator-prey dynamics, which are a biological balancing group, right? When prey, population rise, predator population rise too, which then drives prey population back down. Supply and demand in market is also a balancing loop. When prices rise, when demand exceeds supply, no, when prices rise, when demand is higher, then supply automatically, because demand is now exceeding supply, you'd somehow try to balance the demand and supply by increasing the price. So this is something that is how you try to restore the balance. So here the crucial point, or most real system contains both types of feedback operating simultaneously. This is what produces the complex, non-linear, often surprising behavior that we observe in ecosystem, in economies, in social system. A system may be stable for long periods, held near equilibrium by balancing loops, and then when a reinforcing loop gains the upper hand, it shifts rapidly and dramatically to a new state. Why is this important? Why we are trying to understand this? Just think from the lens that, the Himalayas, the ice melt, all of these that we are now worried about, they have been, creating an equilibrium. They had a kind of a balancing loop. If we keep on, try to bring or try to make them disequilibrium or change that balancing loop, if we keep on doing this, the reinforcing loop can then gain an upper hand, and that may actually dramatically take it to a completely new state. Now, this is where we need to therefore talk about the thresholds and the tipping points, right? So, one of the most important and policy relevant concept actually in systems thinking. So, a threshold is the point at which a system shifts abruptly from one stable state to another, and often irreversibly. And the system may be in a stable state, a clear lake, a stable climate, a productive fishery for a long period, but then because of external pressure builds up gradually. And then at some point, a relatively small additional push crosses a threshold and the system flips to an entirely different regime. An algal dominated lake, a new climate state, a collapsed fishery. The shift can be fast, dramatic, and extremely difficult to reverse. And this is something which is so strongly connected to what we today call it as climate change, because climate change is not something that it has only happened in last 2 decades. If you study climate change and if you look at the work, the literature, that it would say that from industrial revolution itself, the change has started, the climate has started to gradually build. But if we would have kept that rate, if we would have not crossed that threshold, we would not have been in a state, very different equilibrium state where we are today. So, why does this matter so much for ecological economics? Because the standard tools of economic analysis, particularly what you say as cost benefit analysis, assume smooth, continuous, and reversible change. They assume that a little more pollution causes a little more harm, a little more harvesting causes little less fish, and that reducing pollution or harvesting will restore the system proportionately. Threshold behavior violates all of these assumptions. When a threshold is crossed, a small additional unit can cause catastrophic discontinuous change, and returning to the original state, if it is possible at all, may require not a small reduction in pressure but an enormous one, because the system has stabilized now in a new state. And so today our earth has stabilized into a higher temperature. Now bringing it back to where it was pre 1999 is a very, very difficult thing, and we are facing the music. We are not yet able to bring it down despite so much of international treaties and negotiation. So the lesson for policy here is actually sobering. And also let me give you one example, concrete example where thresholds are known to operate. Coral reef, bleaching. Coral reefs survive within a relatively narrow temperature range. Exceed it by even a degree for a sustained period, and the algae that give coral their color and the nutrition are expelled, leaving bleached, drying structures. Soil degradation, agriculture soil can absorb and recover modest disturbance, but beyond a certain level of erosion and compaction or chemical alteration, soil structure collapses and productivity may never recover. Similarly, fishery collapse that we talk about, fish population, as we discussed in lecture 11, can support harvest up to a point. But once they fall below critical dispensation threshold, as we discussed in that MSY curve, the collapse is self-reinforcing. And all of these basically tells us that we cannot always manage our own way back from a threshold once it is crossed. Prevention is not merely preferable to cure. It may be the only option. If you prevent reaching that threshold, then we are much more safer. Now, this also brings us to the concept of resilience, is also one of the most important contribution that ecology has made to policy thinking in recent decades. It is also one of the most frequently misunderstood, concepts. So let me define it carefully. So resilience, in the definition offered by Walker and colleagues in 2004, now these are some of the literatures which you can read as well, is the capacity of a system to absorb disturbance and reorganize while undergoing change, so as to retain essentially the same function and structure. Okay, how much capacity a system has to absorb. For example, how resilient are you to coal? Like, you might be exposed to coal, you might be exposed to many. So you may get fever, you may feel cough and cold, but then you come back to your normal self, right? And then you start your work again. So that's what is about resilience. So as you can maintain the same function and structure. Now, notice what this definition does and does not say. It does not say that a resilient system resists change. It says that a resilient system can absorb change and disturbance while remaining fundamentally itself, while continuing to perform its core function. So, in practice, resilience is discussed at three levels, each appropriate to actually different contexts. Engineering resilience is the simplest. It refers to the speed at which a system returns to its equilibrium after a shock. So, for example, a car's suspension system is engineered to be resilient in this sense. It absorbs bumps and returns quickly to smooth running. That's why we have something like a suspension. If your suspension is good, then it would bump, but then it comes back to your normal situation. So this concept of resilience is useful for designing or design mechanical systems, but it is too narrow for living ecosystems. So ecosystem resilience is more fundamental. It refers to the size of the disturbance a system can absorb before it shifts to a different state altogether. A lake with high ecological resilience can absorb considerable pollution before flipping to an eutrophic state. Like I gave you the example of Ganges as well, it had high resilience. A forest with high ecological resilience can recover from fire, storm damage without losing its essential characteristics. Ecological resilience is about the width of the basin of attraction, how far from the threshold the system normally sits. Is it very close to the threshold or is it very far? So if you are very far, then your ecological resilience of that system is very high. So socio-ecological then goes further still. I mean, I think you must have heard of this concept. So far, we spoke about engineering resilience and ecological resilience. Now, let's think about what is socio-ecological resilience, which goes even a little further. So it basically refers to the capacity of a coupled human and ecological system to adapt, learn, and transform in the face of change. Now, this includes the ability of communities and institutions to respond to new information, to adjust their behavior, and when necessary, deliberately transform themselves into something which is fundamentally different in order to preserve core functions under radically changed conditions, right? So the policy implications here are significant, and it can like run counter to conventional economic wisdom. So basically, managing for resilient often means accepting lower short-run efficiency. A monoculture agriculture system may be highly inefficient in producing one crop under normal conditions, but it is also highly fragile, vulnerable to single pest, disease, or climate shock because it is monoculture. A diverse, redundant ecosystem may appear wasteful by efficiency criteria, but that redundancy is precisely what produces resilience because it is not monoculture, it has a diverse ecosystem, so it has more capacity to be more resilient, and efficiency and resilience are therefore a lot, how would I put it, are trade-offs actually, right? So you might, if you are going ahead with a monoculture agriculture, it might be very efficient because you're producing one crop under normal conditions, but it is highly vulnerable. But if you move to something like which is diverse and redundant ecosystem, it may appear wasteful, but efficient from an efficiency criteria, but it can provide much more resilience. So policy therefore must make a deliberate choice about where on that trade-off it wants to be. And ecological economics argues strongly that we have tilted too far for short-run efficiency at the cost of resilience that we urgently need. So let me just bring these things together and try and explain to you what exactly are we trying to talk about. What is a takeaway from this lecture? The first is, remember that systems behave non-linearly. Small changes can have large effects, and large changes can sometimes have surprisingly small effects until a threshold is crossed, after which a small additional push can also trigger dramatic change. So linear thinking, in which inputs and outputs are proportional, is the wrong tool for understanding these complex systems. Second, reinforcing loops amplify and balancing loops stabilize. So understanding which type of feedback is dominant in a system at any given time is therefore essential for predicting its behavior and designing effective intervention. Third, threshold means that change can be abrupt and irreversible. This fundamentally undermines the assumption of smooth reversibility that underlines conventional cost benefit analysis. So, ecological economic policy must take seriously the possibility of catastrophic irreversible transitions once that threshold is reached. Fourth, resilience is about maintaining function under change, not about resisting change. A resilient system can bend without breaking. Building and preserving resilience is a legitimate and important policy objective, even especially when it conflicts with short run efficiency. So, building resilience, therefore, is very, very important because it doesn't really resist change, but it can continue functioning in the same way even when a change happens. So, therefore, a lot of intervention needs to go to build our forest system, our overall ecosystem more resilient. Fifth and finally, efficiency and resilience are often trade-off against each other, and policy must make conscious choices about where it wants to sit on that trade-off. The current global economy has optimized heavily for efficiency, lean supply chains, monoculture agriculture, specialized production. The resilience cost of that optimization is becoming increasingly now visible. Now, for those of you who want to go deeper into these ideas, I recommend some of these reading. As you see in the slide, these are very important readings if you want to get more into what is socio-ecological system, what is resilience, how can you bring in systems thinking in your work that you are doing, particularly PhD work. I think these are some of very, very good paper which you can refer to and you can read more on. Some of them are very classic paper, as you see, 1973 publications, but these are very good writing to understand or get a deeper understanding of these concepts. So I leave you with a discussion question to reflect on, and you identify a reinforcing feedback loop in your local environment, maybe in your city, your region, or sector where you work, that may be approaching or may have already crossed a threshold. So you can think about it as something that you may like to motivate yourself to read this and come with a answer to this thought-provoking question. Okay, so I'm going to stop here and then we meet in the next class. Thank you.